In this video, we are going to look at what is reactions rate and what is differential rate equation and how to do calculations related to differential rate equation. Hey, I'm Teacher Tan. If you like my video, do remember to click on the subscribe button below so that you won't miss any notification as I update my channel. What is reactions rate? Reactions rate refers to speed of a reaction, or we can define it as the change in concentrations of reagents or products per unit of time. For example, for a reactions where reagent A is being converted to the product B, as the reactions proceed, reagent A are being reacted to form the product B. Therefore, the concentrations of reagent A will decrease with time, while the concentrations of product B will increase with time. And the reactions rate can be measured as the rate of disappearance of reagent A, or can be measured as the rate of appearance of product B. The reactions rate written in the form of the rate of disappearance of reagent A and also the rate of appearance of product B is what we call as differential rate equation. When writing the rate of disappearance of reagent A, there is negative in front to show that for reactant, the concentrations of reagent decreases with time as the reactions proceed. While for the rate of appearance of product B, it is a positive term because as the reactions proceed, product B is being produced and therefore the concentrations of product B increases with time as the reaction proceeds.
Unit for reactions rate is molar per time, and the time can be second, meaning hour, month, or even years. And reactions rate is always inversely proportional with time. So it means that if a reaction takes longer time to complete, means that the reactions has lower reactions rate or vice versa. Now we move on to look at differential rate equation. For reactions with reagent A being converted to product B, we can write the reactions rate in terms of the rate of disappearance of reagent A and also in terms of the rate of appearance of product B. This way of writing reactions rate is what we call as differential rate equation. If the reaction involves more than one mole of reagent or product, how should we write the differential rate equation? For example, in a reaction where 2 moles of hydrogen iodide gas being decomposed to 1 mole of hydrogen gas and 1 mole of iodine gas, we can see from the balanced chemical equation that the rate of appearance of product hydrogen gas or iodine gas is always half the rate of disappearance of reactant hydrogen iodide. Therefore, when we write the differential rate equation, we should write the reactions rate equal to the half the rate of disappearance of hydrogen iodide, which is equal to the rate of appearance of hydrogen gas and the rate of appearance of iodine gas. So how do we get the half? So the 2 here is basically based on the stoichiometric coefficient in the balanced chemical equation. Therefore, we can conclude that if we have a general equation where A mole of reagent A react with B mole of reagent B to produce C mole of product C and D mole of product D, we can write the differential rate equations as reactions rate equals to 1 over A, and the A is the stoichiometric coefficient of A in the balanced chemical equation. The rate of disappearance of A equals to 1 over B, same with the stoichiometric coefficient for B in the balanced chemical equation. Rate of disappearance of reagent B, which is equal to 1 over C, same with the stoichiometric coefficient of C in the balanced chemical equation. The rate of appearance of product C equal to 1 over D, same with the stoichiometric coefficient of D in the balanced chemical equation, rate of appearance of product D. Now we move on to look at how to solve these 3 questions involve differential rate equation. Question A asks how the rate of disappearance of ozone related to the rate of appearance of oxygen appears in the reaction. So this question basically asks us to write the differential rate equation to relate the rate of disappearance of ozone with the rate of appearance of oxygen. So to write the differential rate equation, we just need to refer to the balanced chemical equation. From the balanced chemical equation, we can write the differential rate equations as rate equal to 1 over 2. So 2 here is consistent with the 2 mole of ozone in the balanced chemical equation. So 1 over 2, the rate of disappearance of ozone, which is equal to 1 over 3. So the 3 here is same with the stoichiometric coefficients of oxygens in the balanced chemical equation. So 1 over 3, the rate of appearance of oxygen. B, the question asks to calculate the rate of disappearance of ozone given the rate of appearance of oxygen is 6 times 10 to the power of negative 5 molar per second. So step number 1, we write the differential rate equations first. Step number 2, we write out the information that we are looking for and also the information that are being given in the question. Then step number 3, we write the information that are being given and the information that we are looking for in terms of the relationship in the balanced chemical equation. So how should we write it? So for example, we are looking for the rate of disappearance of ozone. And in the balanced chemical equation, ozone is equal to 2 mole. So we write as 2. And for rate of appearance of oxygen, so oxygen is product, so being formed. So rate of appearance, so having the positive term. And from the balanced chemical equation, it is equal to 3 mole. So 3. So mathematically, okay, so we can do cross multiplying in order to calculate the rate of disappearance of ozone. So that is equal to 3 rate of disappearance of ozone, which is equal to 2 rate of appearance of oxygen. And then we only want to find the rate of disappearance of ozone. Therefore, we can bring the 3 over, become 2 over 3. And for the rate of appearance of oxygen, it is given as 6 times 10 to the power of negative 5 molar per second. Substitute that into the equation to give us the answer. So, which is 4.0 times 10 to the power of negative 5 molar per second. So at the end, we need to write our answer in this form. So the rate of disappearance of ozone, therefore, is 4 times 10 to the power of negative 5 molar per second. Question C asks us to calculate the rate of decreasing in concentrations of oxygen given the rate of decreasing concentrations of reactant nitrogen monoxide NO is 2.5 times 10 to the power of negative 4 molar per second. To do this, first we need to write the differential rate equation. We can write it as rate equal to 1 over 4. So the 4 is same with the stoichiometric coefficient of NO in the balanced chemical equation. So 1 over 4, the rate of disappearance of nitrogen monoxide reactant equal to 1 over 1. So 1 here is equal to the stoichiometric coefficients of oxygen in the balanced chemical equation. 1 over 1, the rate of disappearance of reactant oxygen, which is equal to 1 over 2. So 2, same with the stoichiometric coefficients of N2O3 product in the balanced chemical equation. So equal to 1 over 2, the rate of appearance of product N2O3. So this is our differential rate equation. So step number 2, we need to write out the informations that are being given to us and the informations that we are looking for. So we are being given the rate of decreasing concentrations of NO as 2.5 times 10 to the power of negative 4 molar per second, and the rate of decreasing of concentrations of oxygen is the one that we are looking for. So step number 3 is to write the informations given and the informations that we are looking for in terms of the relationship in the balanced chemical equation. For example, in this question, we are looking for the rate of decreasing of the concentrations of oxygen. And in the balanced chemical equation, it is equal to 1 mole, so 1. And we have been given the rate of decreasing in the concentrations of nitrogen monoxide. And in the balanced chemical equation, it is equal to 4. And then, to calculate the rate of decreasing in the concentrations of oxygen, we can do cross multiplying mathematically. So to give us 4, the rate of decreasing concentrations of oxygen equal to 1, the rate of decreasing concentrations of nitrogen monoxide. And we want to look for the rate of decreasing concentrations of oxygen. So means that mathematically we can bring over to the right the 4 to give us the rate of decreasing of oxygen equal to 1 over 4 the rate of decreasing concentrations of nitrogen monoxide, which is given in the question as 2.5 times 10 to the power of negative 4 molar per second, to give us the answer as 6.25 times 10 to the power of negative 5 molar per second, the rate of decreasing of concentrations of oxygen. We do not stop here. The last step is we write again the rate of decreasing concentration of oxygen equal to 6.25 times 10 to the power of negative 5 molar per second.